Oh, okay. Let's start the second lecture. So, for the next, I think over the next couple of weeks, there are going to be talks at the Field Institute, and a lot of talks are going to be machine learning talks. In particular, 2 weeks from now, there's going to be a whole week dedicated to machine learning. So I think that for that 1 week, I will announce we'll probably do the same thing. There's going to be a talk at 11 o'clock. You're welcome to go to the talk, and the class will start at 12. So, if that happens, come at 11. If you don't see anybody, that means there is a talk, go to the talk. Or just hang out for an hour if you don't want to listen to the talk. Okay, so today we're going to look at the Bayesian models. Let's look at what we've done in our last class. Right? We've looked a little bit at the statistical decision theory. We've looked at the linear regression models, linear basis functions. We've looked at the regularization, as well as touched a little bit upon bias and variance trade-off. Right? And we looked at the bias and variance decomposition from the frequency standpoint. So today's lecture, we're going to be looking at the Bayesian models. How many of you are familiar with Bayesian models? All right, a few. That's good. In particular, we're going to be looking at Bayesian models, Bayesian linear regression models, and such. But I'll try to explain a little bit, give you a little bit of background of what these models are. Okay. By the way, I should point out there is an excellent tutorial by Redford Neal on Bayesian methods for machine learning that I encourage you to look at, and it should be on the website. Okay, so what's the idea behind the Bayesian approach? Well, we want to formulate our knowledge about the world probabilistically. Okay? So the first thing we need to do is we need to define a model. And we're going to put our assumptions when we're defining a model, such as some independence assumptions or framework distributions and such. So that's something that a statistician or machine learning person will have to define. And typically, the models that we're going to be working with will have some unknown parameters. Right? What we're going to do is we're going to capture our assumptions or our beliefs about the parameters of those models by specifying a prior. So, for example, range of possible values and such. We're going to be specifying the prior distribution of those parameters before we actually get to see the data. Okay? And I'll make, we will go through some examples of that. Then we get to observe the data, and we compute something that's called the posterior distribution of the parameters given the data. Okay? And then we can use this posterior for making predictions. Right? And essentially what we're going to be doing is we're going to be making predictions by averaging over the posterior distribution. We can examine and account for uncertainty in the parameter values by looking at the posterior distribution. And we can also make decisions by minimizing expected posterior loss. Okay? So one of the key components in the Bayesian approach is the posterior distribution. So let's look at the posterior distribution. So the idea behind the inference, Bayesian inference, of computing the posterior distribution is that you can get it by combining the likelihood for the parameters with the prior. So two things. There's a likelihood of the data, given model parameters. There's a prior of parameters, and you essentially combine the two. And the way you can combine the two is by using Bayes rule. And we've seen a little bit of Bayes rule in our last class, where we can define it as follows. We say, well, the posterior distribution of the parameters given the data equals 2, and that's just a mathematical definition. Probability of the data given parameters, that's our model, that's something that we have to specify, times the prior of the parameters, that's something that we have to specify as well. Okay? In terms of what we're going to be writing in terms of sort of a different notation, we can say, well, the posterior distribution, this is called the posterior probability, posterior distribution over the parameters W given the training data. This is probability of observed data given the parameters, given the W. This is the prior probability of our parameters, of the weight vector W. And this is sometimes called marginal likelihood. Right? This is the probability of the data, where we essentially integrating out over the parameters. If we're working in discrete space, that's just going to be summation. Okay. Sometimes people call it normalizing constant. The reason why it's called normalizing constant is just it doesn't depend on parameters. So effectively, given a particular data set, it's a constant, but it ensures that the posterior probability here integrates to 1. Because we want to get the distributions, probability distributions out. Okay. Now, this integral here can be very high dimensional. And in practice, when we work with real models, this is going to be a high dimensional integral, and it's going to be difficult to compute. Right? So essentially what we have here, this is something that we assume we can compute. Given the parameters, can you compute the probability of the data given parameters? This is the pri. Typically, we assume some form of the pri we can compute. This is the term, the marginal likelihood is something that we cannot compute because it implies this integration of a high-dimensional space. So that object is a very important object of interest to a lot of Bayesians when we do Bayesian inference. When you look at the papers, occasionally people say, well, how do we estimate marginal likelihoods? How do we compute them? And so forth. Okay? And that really just comes out from the basic rules of probability. But it's just coming out from the sum rule and just from the product rule. Now, how do we make predictions given the posterior distribution? Well, the Bayes rule in words, we can also sometimes we can say, well, the posterior distribution is proportional to likelihood times the prime. Right? In words, that's generally, you hear a lot of people when we talk about Bayesian inferences, it's the case that the posterior distribution is proportional to the likelihood times the prime. Now, how do we make predictions for a new data point, x star, given the training data set? And the way we can do it is we can integrate over the posterior distribution. And again, if you look at this formulation, I encourage you to look at it more carefully and look at the book. But it's a very sort of simple mathematical formulation here. There's no magic. So here, you're specifying what's the probability, what's the probability of test data point x star given the parameters and given your training data set, times the posterior distribution over the parameters, and you're integrating over the parameters. The other way of looking at the predictive distribution is you're looking at the expected value of the probability of observing the data given the parameters, where the expectation is taken with respect to posterior distribution. It's the same thing. Now, this is sometimes also called predictive distribution. That's what you actually need to do to make predictions within the Bayesian framework. Essentially, you have to compute these expectations. Now, one of the challenges here is that if you want to compute predictive distribution here, you have to know the posterior distribution. It requires the knowledge of the posterior distribution. Yeah, there's a question?
Yes. In your W's there for your predictive distribution, are those the maximum likelihood estimates that you're plugging in at this point, or is that just...
Good question. So the question is, I'm not talking about the maximum likelihood estimates here. If you think about maximum likelihood estimates, we'll get to that as we go through the class. Maximum likelihood estimates, you can think of W as a point estimate. That would be your maximum likelihood estimate. So if you're trying to do maximum likelihood, typically your parameters, you'll have a point estimate in the parameters. Right? In this case, you can think of it where we have the whole distribution over the parameters, right? As opposed to making a point estimate. But we'll look at the relationship between the two as we go through the class. Mm-hmm. Good question. And again, if we look at, computing predictive distribution here requires us to know the posterior distribution of the parameters. And again, if we look at the posterior distribution of parameters, this integral comes to play, right? It's the marginal likelihood. And again, we're dealing with high-dimensional integrals. In a lot of practical problems, this is something that we'll not be able to compute exactly. And that will be a challenge, computation. In fact, if you look at this equation here, you have to sort of compute this integral, high-dimensional integral, and then you have to compute this integral, which is also would be high-dimensional. Now, let's look at some of the modeling challenges. The first challenge is in specifying a good model. Okay? That's always a challenge. Everybody has to do that in the field of statistics or machine learning. But then you also have to specify a suitable prior. And specifying prior distributions could be challenging, particularly when you're dealing with high-dimensional problems, right? Such as the problems that you see in machine learning. Now, a suitable model, a good model, should admit all the possibilities that are thought to be at all likely. So you want to design a model such that this model actually gives some probability to events that can happen. A suitable prior should also avoid giving a probability 0, a very small probability to possible events. That's something that you have to design a priori. If you're measuring something, some quantity, and you're saying a priori, I believe that the probability that this quantity between 6 and 5, for example, is almost 0, and it happens to be between 5 and 6 in reality, then you're in trouble. Because you'll have to get a lot of evidence to override your prior. But at the same time, you also want to design prior probabilities that should avoid spreading out the probabilities of all possibilities. So you should avoid having a prior that's too broad, because then you're losing information. It's not very informative. So you might have to have a property such that the dependencies between parameters are not too spread out, or avoid having a prior that is too spread out. And there are several ways of doing it. One strategy is to introduce latent variables. It's something that we're going to see in the second half of this class. We're introducing latent variables into the model. And the second choice is defining hyperparameters, or specifying hyperparameters and putting them into your prior. So models like hierarchical Bayesian models is, for example, one way of doing that. And we'll see examples of that. So both of these ways essentially represent ways of modeling dependencies in a tractable way. Okay, but this is a challenge. There are no sort of magic tricks and such. This is something that you have to design yourself as you look at the data and you deal with the data. Now let's look at computational challenges. The second big challenge is actually computing prestige distributions. And that actually was the reason why Bayesian methods were not very popular up until, I guess, the early 90s in practice in general, because a lot of these models are actually computationally very heavy. So there are several main approaches to compute the posterior distribution. The first one is called analytical integration. And in this case, if we use so-called conjugate priors, then the posterior can be computed analytically. So the very first thing we can do is we can specify certain types of priors. Now, these priors might not reflect our beliefs about the world or the parameters, but at the same time, a lot of people are using conjugate priors because that makes computations be analytically tractable. Right? So you can compute things exactly. We'll see some of that. It only works for simple models, and it's usually too much to hope for. So generally speaking, this is something that you can do, but it's fairly limited. A second class of approximations that was popular in the 90s is Gaussian or Laplace approximation. So here, you approximate the posterior with a Gaussian distribution, and it works fairly well when there is a lot of data compared to the model complexity. The reason for that is, as the data size grows, typically posteriors will be close to a Gaussian distribution. We'll see some of that in the next class, how we can actually use Laplace approximation there. Yeah?
Does this mean that your prior is also close to a Gaussian, or is this?
The prior doesn't have to be close to a Gaussian. Right. It's sort of like a law of the central limit theorem sort of kicks in as you get more and more data.
But does it not matter when you choose your prior?
No. It's just that whenever you get a lot of data, a lot of observations, you can show that the posterior is going to be fairly close to Gaussian. Now, Laplace approximations are used from time to time, but again, it's sort of it's fairly limited way of approximating the posterior. I think one of the dominant methods today is something that's called Monte Carlo integration, Markov chain Monte Carlo. And the idea behind Monte Carlo methods is that if you actually get a sample from the posterior distribution, right, you're actually able to get a sample from the distribution, from the posterior distribution, then you can do a lot, right? Such as, approximate the predictive probabilities and estimate uncertainties and such, if you can get a sample. And the dominant approach today is Markov chain Monte Carlo, where you're simulating a Markov chain that converges to the posterior distribution. And as it converges from the posterior distributions, you can draw samples from that distribution. It's a very sort of flexible set of models, can be applied in a variety of problems. If you look at statistics or machine learning, there's a whole field dedicated to MCMC methods. How do you design them? How do you construct them? Various different variations and such. It's a pretty big field in statistics and machine learning. And the last one that's also fairly popular today are the variational approximations. These represent a much clever way of approximating the posterior distribution, which doesn't involve sampling. It often works much faster compared to MCMC, but it's often not as general as MCMC. And there is some sort of theory behind these two algorithms. Variational approximations, they are to some extent biased because you can never recover the true posterior distribution. MCMC gives you asymptotic guarantees that for certain under certain assumptions, eventually you'll be sampling from the posterior distribution. But again, if you look at the field of machine learning in particular, the whole group of people working on variational approximations. And we'll see some of that again at the second half of the class.
What's the intuition behind this variational approximation?
The idea behind variational approximations is that you can try to approximate, let's say, the posterior distribution, either using an approximate distribution, some other distribution. So, for example, fully factorized distribution that leads to something that's called mean field approximation. So you don't know exactly the posterior distribution, but you try to come up with the distribution that's as close as possible to the true distribution, true posterior distribution, but which is approximate. And yet there you have to make certain assumptions, like it's fully factorized, or it has certain forms and such. Yeah, question?
I'm kind of curious where the name comes from.
Variational approximations?
Yeah.
I think the variational approximations, I think that the whole set of algorithms here comes to us from statistical physics. Field approximation, that's right. Data approximation and such. The statistical physicists were working in that area a lot. Primarily, my guess is that they wanted to have algorithms that would work much faster compared to MCMC. Now let's look at the Bayesian linear regression model. Here's one example. This is one of the simplest examples where we can make things be tractable. Okay. So given observed inputs, x1 to xn, and the corresponding target values, you can write down the likelihood function. This is something that we've seen in our last class. Under IID assumption, these phi's here, these are representing our basis functions, right? So we have n basis functions. Now, we can look at the conjugate prime over the parameters, and we can say, well, the prime distribution over the parameters here, w, are going to be given by a Gaussian distribution, normal distribution with mean mu sub 0 and some covariance matrix S sub 0. Now, both the likelihood and the prior is Gaussian, right? The likelihood is Gaussian, the prior term is Gaussian. So the posterior distribution will also be Gaussian. Right? That's just one of the things that if you multiply Gaussian likelihood by Gaussian prior, you can show that the posterior is actually Gaussian. I think on one of your homeworks you'll actually derive it analytically yourself. So that comes, that gives us a definition of conjugate prime. Right? If the posterior distribution over the parameters is in the same family as the prior distribution, then the prior and the posterior are sometimes called conjugate distributions, conjugate over chain. Right? And the price is called conjugate phi for the likelihood. So this is sort of a useful thing because all of a sudden you know that the posterior is Gaussian, so you can compute it exactly.
Sorry, M naught and S naught are fixed.
The what?
The M naught and S naught are fixed.
That's right. M naught and S naught are fixed, and that's something that you have to specify. That's your prior belief, what the mean of your parameters vector should be, and what the prior covariance should be. Common choice you see a lot is zero mean identity covariance, for example. Right. Now, if you look at the posterior distribution, then we're combining the prior with the likelihood. So this is our likelihood function. We're multiplying it by the prior. So the posterior is being proportional to that. And the posterior, with a little bit of manipulation, takes the following form. So the posterior here is going to be given by, again, a Gaussian distribution with mean and the precision matrix. So sometimes I'll have a term for the covariance matrix, and the precision matrix is just going to be the inverse of the covariance matrix. It's the same thing. Okay. So now if you look at these equations, they sort of might be a little bit mystical. So there's some numbers. So let's dig into them a little bit. And one thing you can see here is that if you look at the posterior mean can be expressed in terms of the maximum likelihood estimator, or the least square estimator, and the prior mean. Okay, so that's first relationship between the two. Remember our maximum likelihood estimator. We were trying to solve this problem using least square or using maximum likelihood estimation. That would be our maximum likelihood estimator. Right? If you look at the posterior mean, I can write it in terms of the prior mean and the maximum likelihood estimate. Okay. Weighted by precision, prior precision, as well as the noise. One thing you should notice here is that if we increase our prior precision, we decrease our prior variance, so we increase this term here, then we're going to be placing a much bigger weight on the prior mean relative to the data. Let's say my prior mean is 0. I think that in my model, zero weight vector a priori is a reasonable choice. Okay. If I increase the precision and I say I really think it should be zero mean, right? You would need more data to override that decision. If you only get to observe 3 data points or 4 data points, and this decision term is fairly high, then you will be pushing your estimate, your posterior mean towards 0. Now, let's look at an easier example. Suppose that we have a 0 mean spherical Gaussian prior, which is governed by a single precision parameter alpha here. So the prior is going to be given by 0 mean and precision alpha. Now, the posterior is going to have this form. Okay. You can just plug it in. And one interesting thing happens here. If you consider alpha going to 0, which essentially means that your precision is becoming very, very precise, so if your precision goes to 0, which basically means that your variance becomes very big, right? So you have very, very small precision, or in other words, your variance becomes very large, prior variance, then the posterior distribution reduces to the maximum likelihood estimator. And that's exactly, that's exactly what's happening here. If alpha goes to 0, then remember, this posterior mean will exactly become the maximum likelihood estimate. You can just plug in the inverse of that here, betas will cancel, and you'll get the maximum likelihood estimate. Now, what this actually means is the following. If you have an unformative prior, at least in this case, if you're saying your prior variance is essentially very big, then your posterior mean is just going to be the maximum likelihood. You're going to be trusting your data more. That's the idea here. And if you look at the log of the posterior distribution, the log of the posterior distribution is going to be given by the log of the likelihood term and the log of the prior. And if you look at that quantity here, and you maximize it with respect to parameters downloading, so if you're interested in map estimation, then it's exactly equivalent to minimizing the sum of squares error function plus the quadratic penalty term. And we've looked at that regularizer before. So it's another connection between the two approaches. Sometimes people don't, typically Bayesians don't think of this as Bayesian model. They think of this as, optimizing penalized likelihood function. If you have a likelihood function, you penalize it. But these are connections between the two. Now, let's look at an example of Bayesian linear regression model, how it's done in practice. So suppose I have just a simple linear model of the form W0 plus W1x, right? That's a simple linear function here. And the way that I'm going to generate the training data is I'm going to be generating it from this function, A0 plus A1x, where A0 and A1 take particular values, and then you're essentially choosing xn uniformly between -1 and 1, and you're evaluating this function, which is a true function, at those values, plus a little bit of Gaussian noise. So let's say this is how the data is generated, and the goal is to recover A0 and A1 from that data. So let's look at how this approach would work here. Suppose we get to observe 0 data points. We don't observe anything. So the prior, in our case, is going to be spherical Gaussian, right? And if we actually look at the data space, these are all possible hypotheses. Right? These are all possible things. Now, let's say we get to observe one data point. Okay. If we observe one data point, it turns out the likelihood becomes constrained over here. So these values are plausible. And then if you look at the prior, so you're combining this likelihood with this prior, that's going to be the form of the posterior. Okay. If you look at the data space, this is where we get to observe the data point. Right? And if I look at the posterior and we sample from the posterior, these are all possible hypotheses. These are all possible lines. Right? That makes sense. Right? If we get to observe the second data point, this is the likelihood of the second data point. We get to combine it with this term here, and we get to combine both of them and the prior. This is going to be the posterior. And if we look at the space of possible samples from, if we sample from that posterior and look at the lines, this is how they would look like. So these are all plausible answers here, right? And notice as we get to see more and more data points, look at the posterior distribution. The posterior distribution sort of focuses on one particular value, right? It becomes more and more peaked. And in this case, in this particular example, as we get to observe more and more data points, or a very large number of data points, you essentially recover the maximum likelihood estimate. The two estimators will converge, just because this value will converge to the maximum likelihood estimate, and this peak will become very narrow. Now, let's look at the predictive distributions. So how do we make predictions? For a new input vector x, and essentially what we need to do is we need to integrate the posterior distribution. Right? Now, let's look at the predictive distribution. Let's parse this out. What I want to do is I want to make a prediction for a new x. I want to predict a new target. Given x and t, these are my training data, training inputs and training targets. And the way I'm going to be making the prediction here is that probability of the target given the parameters and given the input. And then I want to look at the posterior distribution for the parameters given the training data. Okay, training TX. It turns out that the posterior distribution is going to be Gaussian again. There's no surprises here. So the posterior mean is going to have this form. The interesting thing to look at, and we've derived that before, the interesting thing to also look at is look at the predictive variance, the variance of the predictive distribution. This term here. that term tells you something about uncertainty in your predictions. Right? So the first term, the variance here, is the noise in target values, beta. Again, beta is something that we cannot, it sort of represents an irreducible noise, right? This is a noise in your observations. You can't go beyond that noise. But this term here is the uncertainty associated with parameter values. It just falls out of that equation. One thing to note here is that as n goes to infinity, the number of data points, the number of observations becomes very large, this term goes to 0. Okay. Now, why does it go to 0? Any guesses? Let's look at this term. This essentially represents, phi transpose phi. Or in other words, if we're dealing with just a data, that would be x transpose x. Right. So as n becomes large, this term will grow. This one will become larger and larger. It's proportional to the number of data points. If this term becomes larger and larger, the inverse of this term here essentially will be smaller and smaller. So you can show that this term will be approaching 0 as you get to see more and more data. And that should make sense, right? Effectively, what this is saying is that for that particular model, as you get to see more data, the predicted distribution will shrink. Uncertainty in the parameter values will shrink. So your posterior distribution will be highly picked around one particular point, and all the uncertainty about those parameter values will shrink. Yeah.
Sorry, I must have missed it. What's actually in the matrix file? Is that just the basis functions that each have?
That's right. These are just basis functions. Think of this as you have a data point, you have a data matrix, X, which is n by d. So that would represent covariance of your data. Now, if you look at the predictive distribution, again, if you look at the two, remember we'll look at the maximum likelihood estimate, and this was our predictive distribution. If we look at the Bayesian predictive distribution, if you look at the uncertainties, this particular model is able to do a little bit better in terms of generalize a little bit better in terms of uncertainties. So it puts a little bit bigger uncertainty. I think this is one standard deviation from my standard deviation. So at least it captures the truth here. The maximum likelihood estimate is not able to capture it here. Now, let's look at the predictive distribution. Let's look at the samples from the predictive distribution just to get a little bit better idea of what is happening here. Remember, we've looked at the sine data set, sinusoidal data set in our last class, right? It's just a curve. If I get to see one data point, and I look at my predictive distribution, my predictive distribution is going to look like this. This is the mean, right? And this is uncertainty associated with my predictive distribution. And this is the green curve is the truth. So you're essentially saying, yes, I think there should be less uncertainty here, that's my estimate, or at least that's my predicted mean, and there is a lot of uncertainty here. If I sample from this predicted distribution, so the way you think about sampling here is that if you sample from the posterior distribution, given this one data point, you'll get some parameters. Given those parameters, you essentially look at the corresponding curve. Right, so I think this, in this case, this is a 9-degree polynomial. So you can see just given one particular observation, these curves are all probable under the posterior distribution. Right. If I get to observe 2 points, that's going to be my predicted distribution. And if I sample from the posterior, these are my samples. This is how my samples would look like. If I get to see, I guess in this case, 4 data points, Notice the interesting thing here, if I get this equal data points, there's a lot of uncertainty here. And there's a lot of uncertainty here. There's less uncertainty here. And that's what you expect to see. If you look at the samples from the posterior, these are plausible samples from the posterior. If you look at that particular curve, right? It's a plausible curve.
So can you remind me what the distribution is on the left that we get a sinusoidal function from? And you're right.
So
this is just some distribution on sine space or something like that? Or?
well, this comes from our example in our last class, right, which comes from a 9-degree polynomial. So this is the function, the 9-degree polynomial, that's our function. That's right, we're just looking at the posterior distribution over the coefficients of that 9-degree polynomial. And the interesting thing here is if you get to observe a lot of samples, right, the red curve here is the predicted mean, and that's your estimate of the variance. And these are samples from the posterior, so all of these curves are plausible samples from the posterior. So it gives you a little bit of notion of uncertainty, which is a useful thing to have. Because it essentially says if you sample from the posterior, you can actually see how your estimates of this 9-degree polynomial, or the coefficients of this 9-degree polynomial. Any questions? Now, one other thing you can do is you can extend this model a little bit. It's commonly done in practice as well. So far we've made an assumption that the noise parameter theta is known. This is whenever you specify the likelihood function, we've made an assumption that the noise is known. However, if the parameters and our noise data, if we treat them as unknown, then we can also introduce another conjugate prior. It's a very useful prior to know about. It's called Gaussian gamma prior, Gaussian gamma distribution, and the idea is that we can specify the joint prior with the parameters and the noise term, which is going to be given by a Gaussian times the gamma. The gamma distribution is given by this expression here. Again, for those of you who've taken stats classes, this is sort of the basic, one of the basic distributions, gamma distribution. The reason why it's also called a useful distribution to know about is if you look at the posterior distribution, the posterior distribution takes the same functional form as the prime. Right? So the posterior distribution here is going to be, the posterior distribution of the parameters should be a Gaussian times gamma. Okay. Now, so this particular form, again, I think in one of your homeworks you'll look at gamma Gaussian distribution, so you'll derive a few things. A lot of people are using that particular prior, again, just because it's computationally tractable. You can compute posterior distributions, you can make all the calculations, you can make predictive probabilities, you can compute everything with that particular conjugate prior. Now, one of the things that's useful to know about these types of models is that if we look at the predicted mean can essentially be written in this form, where I can look at phi transpose S sub n phi, and I can think of it as a kernel. So the mean of the predictive distribution at a particular data point x, or time x, can be written as a linear combination of the training set target values. Okay. And these kinds of regression functions are called linear smoothers. Right? Because essentially, anytime you want to make a prediction of a particular data point, you can essentially think of it as you look at all of your training targets and you reweight them. You reweight them according to this particular formula. Sometimes this is called, that defines a kernel of curves. You can think of it how similar x is to xn. So this is, we'll come back to that point when we look at Gaussian processes. that showed very closely there. But again, these are just linear smoothers. So you look at the points that are nearby with some, you define some form of kernel that tells you something about how close the input points are, and you look at the weighted average of those. If you look at the kernel as a covariance function, if you look at the covariance between the two targets or the two predictions, then the covariance has this form. And again, we can think of it as defining a kernel function between the 2 points. Now we can avoid the use of basis functions. Everything now is being done in terms of these basis functions. We can essentially define the kernel function directly, and this is something that leads to a Gaussian process. Again, it's a generalization of these Bayesian linear models, and it allows for a much more flexible class of models. And again, this is something that we're going to look at this class at the second half of the class, once we get there. Now, the second point that I should make in this class is the Bayesian model comparison. That's another very big topic in machine learning and in statistics. Is as follows. So suppose we have a set of L models, M1 up to ML, and we want to compare them on a particular training set D. We can specify the prior distribution over different models. And given a particular training set D, we want to evaluate the pastivity. So the pastivity distribution, if we want to pick one of the models, the pastivity distribution of the models is going to be given by the prior times, in this case, this is called model evidence, and again, it comes down to the notion of the marginal likelihood. Now, for simplicity, let's make an assumption that all models are a priori equal. And that actually becomes one of the very, key problems in machine learning. If you have multiple models, how do you choose one, for example? Or do you average them somehow? Now, if we assume a priori that all models are equal, and in this case, the model evidence essentially looks at the preferences shown by the data for different models. So here you're basically saying, what's the probability of the training data given model 1? And what's the probability of the training data given model 2? What's the likelihood of the data under this particular model? Now, if you look at the ratio of the two models, or the ratio of the two model evidences, this is sometimes called base factors. You look at the ratio between the two, and you can say, well, how likely one model over that, how likely one model explains the data more compared to that model. Now, there's no good way of doing model selection. There's a lot of research on base factors. But this is one term that you will hear a lot if you look at statistics or statistical machine learning. Okay. Now, let's make an assumption. Let's say once we compute the pastivity distribution, let's say we can compute the pastivity distribution of models, then we can compute the predictive distribution. So how do we compute the predictive distribution? Well, that's the same thing. The posterior or the predictive distribution of a particular target given a test point x is going to be given by this expression, which is the likelihood of the target given the test point on the model, who's at m sub I, multiplied by the posterior probability of it. So essentially doing Bayesian model averaging here. The overall predictive distribution is, again, you're going to be looking at averaging the predictive distributions of individual models, weighted by the posterior probabilities. One key thing about Bayesian model averaging here is that if you have two models, and let's say one of the models predicts the target given by A, the other predicts the target given by B, your predictive distribution is going to be bimodal. That's the key. Right? So whenever you're doing Bayesian model averaging, again, it's typically going to be multi-modal with different models make different predictions. Now, a simple approximation, again, that's commonly used in practice is just a model selection, where you're effectively trying to find a single model, right, with the highest evidence that gives the highest probability to the data. Yeah, question?
Is there one over L missing some, or?
No, I don't think there's one over L, because here you're looking at the probabilities, right? So these guys sum to 1. Right. The posterior probability of the models, if you sum these over MIs, these sum to 1. So for example, if each posterior probability of each model would be equal, then you'd have 1 over L. And you just do the standard averaging. Right. And also in Bayesian model averaging, what typically happens is that if you get more and more data as n goes to infinity, the hope is that the posterior will be picked around the true model, or will be picked around the correct model, in which case you'll just be using that model for different predictions. Now, remember that the posterior distribution is given by the evidence times the prime. If we have models, and we will have models where we're going to have set of parameters W, the model evidence is going to be given by this expression here. So let's look at this expression. It's the likelihood of the data on the model MI, given the parameters, times the prime over the parameters, given our model, and we integrate it over the parameters. That's the evidence of the model. So here we have to integrate over the parameters. One key thing here is that the evidence is essentially a normalizing term that appears in our base rule when we compute the posterior probability. So in order to compute the posterior probability, the denominator is the evidence, the marginal likelihood. And that's the marginal likelihood that sits in here. We want to compute the posterior distribution of parameters. So this marginal likelihood sort of pops up again and again, right? You can think of the marginal likelihood again as the evidence that the model gives to that particular data set that you're looking at. And this is also called marginal likelihood, as I mentioned before. So that's why that's one of the sort of key, one of the key concepts in Bayesian statistics. How do you approximate? How do you compute this evidence? There's a lot of research in that area. Now let's get some insight. What is happening with these models? That will help us understand a little bit the relationship between pi and the posterior and how pi can affect the evidence. So let's make the following assumption. Let's say we're looking at the model with a single parameter W, and we're making the following assumptions. We assume that the posterior distribution here is going to be picked around the most probable value W in that. Okay? So this is our posterior distribution. It's going to be flat here, and it's going to be picked around that particular point. We're also going to make an assumption that the pi is flat, and the width of the pi is delta W pi. And the width of the posterior is that delta W posterior. So this is the pi. You can think of it as just pi probability over minus W. This is the posterior, given the data. Now, yeah.
When you say around the most probable value, probable with respect to what?
Just think about it. We'll come to the map estimate, but think about this as just some point. Right? Think about the posterior is going to be picked around this area.
Oh, so it's just a mode.
It's just a mode. Think of this as just a mode. It's just going to be picked. It's just a mode. Pick that particular W. Your price says a priori this could be. These are plausible values for your parameter. A posteriori, once you get to observe some data, this is going to be the posterior distribution. It's going to be just a single mode of the posterior distribution. So now, if we look at the marginal likelihood, right, and we integrate this likelihood function times the phi, this integral is going to have 0 probability here. This integral is going to have 0 probability here. because the probability of the data under those W's, under those configurations of the parameter W is 0. And it turns out that this is approximately going to be equal to the probability of the data given a mode, the W map, it's there here, times the delta of the posterior divided by the delta of the prime. So this looks at the ratio of this term, the delta of the posterior, the delta of the prime, times the peak. And if you try to estimate this integral, you do immediately see that that approximately holds. Yep.
To get the width of those distributions, do you just use the standard deviation, or?
So under this assumption, we're just making an assumption that that holds. That might not necessarily hold in practice. We're just making an assumption that a priori you have uniform prior, some width. A posteriori, the posterior distributions just have a smaller width with some height. This is just so that we can compute this integral explicitly. Now, if we take the logs, this is an interesting thing that we get. If we're taking logarithms, we're going to have the log of probability of the data given the parameters times the log of the ratio. Now, notice that the log of the ratio is going to be negative, because this ratio is always going to be less than 1. Right? Obviously, your prior is typically broad, your posterior is going to be picked. Yeah, is the question?
Yeah, sorry, I don't, this P and D, that's just for that you see some observation.
Probability of D, yes, so this is probability of observing D. D is your data set.
But on the other side, you have P and D conditioned on this W map.
That's right.
W map is not fixed, it's a random.
In this case, let's make an assumption that it is fixed.
So you've done all your work.
You've done all your work, it's just some parameter W that's fixed.
Okay, so on the left-hand side, it should also, this is conditioned on knowing what this W map is, basically? No.
Say that again, sorry?
On the left-hand side, you also know what this W map is, or?
Yes, you know what the W map is. It's just 0.3, let's say.
You've done all of it.
You've done all the computations, yes. So, this is the term, what's the probability of the data given the most probable configuration of the parameters? This term is negative. Now, if we have m parameters in the model, we're going to be making assumption that this ratio is the same, then what's going to happen is that if you look at the evidence, approximately, it's going to have this term plus this term multiplied by m. So it's going to be negative and it's going to be linear by m.
Can you explain why that holds? That statement formula?
This term here?
No, why do you get this formula from the first?
From the first? Oh, because if you model, so this model was derived for just one dimension, right? If you have m parameters in your model, so let's say you're working with an m-dimensional model, right? Then you're just going to be multiplying this term by m. You're assuming that this ratio holds roughly across all dimensions. Again, this is just an example. It's just an approximation, right? Because obviously in reality, different dimensions might contribute differently. But roughly speaking, this term is going to be negative, and it's going to be some linear function around the dimensionality of the problem. Now, this is the key sort of equation when we look at the marginal likelihood, because it tells us the following. If we increase the complexity of the model, right, if the number of parameters, increase the number of parameters in our model, or the number of adaptive parameters, the first term will increase. It will increase the probability of the data given the model. Think of our 9-degree polynomial function, right? If I choose second-degree polynomial, you will fit the data. If I choose 9-degree polynomial, I can fit it perfectly. So roughly speaking, as I increase the number of parameters, this term will go up. And that's always the case. If I get to observe 1,000 data points, I fit a 1,000-degree polynomial, I can fit the training data perfectly. So as I increase the complexity of the model, I can make this be, can make it larger and larger. Whereas the second term will decrease due to this dependence on the number of adaptive parameters. So that represents one of the sort of key aspects, because what happens here is that the optimal model complexity, the optimal model, is you're going to be looking at the trade-offs between these two competing terms. It's penalty coming from the prior, and how flexible your model is. So here's another example, maybe another way of thinking about this is, so in this particular case, we have a space of data sets, and we have the space of marginal likelihoods, or probability of data sets under different models. Now, for a particular observed data set, these are not. Right? The model M2 with intermediate complexity has the largest evidence. Now, this is a cartoonish example, but it essentially communicates the following picture. The simple model, let's say this is your simple model. Let's say these are classes of linear models. These models cannot fit the data well just because they are too simple. Whereas two complex models, or more complex models, it spreads its probability mass across the whole range of data sets, the whole range of data points, and so it basically assigns fairly small probability to each one of them. Right? So that has another way of thinking about it. You have a simple model, you can't explain the data. So your first term, you're not going to fit the first term. If your model is too complex, it's going to give small probability to a particular data set that you're looking at because it's so flexible, it can explain everything. Right? So models with intermediate complexity is when, for a given data set, is the one that you should be choosing. Now, one thing I should point out is I put this in here is that the marginal likelihood is actually very sensitive to the prior that's being used. So you have to be very careful how you use your marginal likelihoods. And computing these marginal likelihoods makes sense only if you're very sure about the choice of the prior. That's just from a practical standpoint, something that you have to be careful about. In theory, everything works out nicely because your prior is your prior belief, it's something you can specify. But in practice, it can be very sensitive to the choice of the prior used. Now, let's look at the framework of evidence approximation. And this probably be sort of the last piece of the class today. If we look at the fully Bayesian approach, we would also like to specify the prior probability over our parameters, or over the hyperparameters. Right? So let's look at the fully Bayesian approach. So if you look at people who really truly doing Bayesian inference, you have a prior. Prior will have some parameters, so you have to specify prior over those parameters if you're not sure about those parameters as well, and try to integrate over this whole space. So if you look at the predictive distribution, we have likelihood, right, in our model. This is a linear model. We have, in this case, posterior over the parameters, posterior over the weights of the model. And then you have these hyperparameters. Right? The hyperparameters tell you something about the noise, how much noise you put in your likelihood, versus how the prior with W is also Gaussian with mean zero and precision alpha. But what if you don't know how to set this alpha? Then there's a posterior over the hyperparameters, and you want to integrate over this entire space. That would be sort of the true Bayesian approach. Right. So just as a reminder, these are the targets, these are the inputs in the test set. These are the precision of the output noise. This is precision of the prior, how broad or how picky your prior is. And this is just representing your training data the inputs and the targets. So here's it.
How would you know when to stop? You can have a posterior over your hyperparameters, you can have more hyperparameters and more and more and more.
Yep, that's a valid question. There is no good answer to that. Typically, I've seen in practice people go into levels of the hierarchy, sometimes 3 levels of the hierarchy. So, you basically say, well, I'm trying to solve a Bayesian linear regression model. I want to specify the prior over the parameters W. I want to specify the prior, well, it's going to be Gaussian with some mean and some variance. Right? I typically think mean 0 is reasonable because a priori you're just predicting 0. But how much should I trust that it's 0? That's specified by the precision. In this case, it's alpha. What this alpha should be? Should it be 1? Should it be 10? Should it be 1,000? It's something that you If you have a good knowledge about what you're trying to model, you can specify it. If not, you can say, well, maybe I'm going to put some prior of an alpha. Let's say I'm going to put a gamma prior. Gamma 1, 1, which effectively can say, yeah, maybe it should be around 1, but it could be also 5, or it could be 10, or it could be 0.1. There's some distribution. Again, these are some modeling assumptions that you have to make. So going into 2 levels of the hierarchy is typically flexible enough for you to infer what the question should be. Yeah.
And just to follow up that question, what would stopping actually look like? Like, is stopping when you say, okay, and then this type of parameter is normal 0, 1, and then you run out of parameters to put prior distribution on?
Well, it's a tricky question. Generally speaking, you can go to multiple levels of hierarchies. Again, there's no good answer. Typically what I see is that people specify 2, 3 levels of the hierarchy, and then somewhere at the top, you might specify, normal 0, 1. But the idea behind these Bayesian models is that whenever you think about the problem and you specify a prior, or you specify the prior with the hyperparameters, you should at least inject some knowledge about what kind of data you're modeling or what you think are the reasonable assumptions. Right? That framework allows you to do that. If you don't know anything a priori about the problem, right? No assumptions on the values of your parameters or even the range of the values, then you can put maybe an informative price or maybe a vague price and such. But generally speaking, when you go to multiple levels, you should think about what kind of price you want to specify. They will affect your decision, and they will affect the model assumptions.
And just a quick, is the name for this hierarchical Bayesian model, or is that a different thing?
So we'll go to hierarchical Bayesian models. You can think of them as hierarchical models as well, because you specify the prior, you specify the prior over the hyperparameters and so forth. But hierarchical Bayesian models, typically you also can introduce some structure. Right now we're just looking at the flat type of representation. In many cases, when people think about hierarchical Bayesian models, you can put some hierarchical structure to specify these prior distributions. Especially have different groups or different populations and such. Good questions. There was another question then. Yeah.
In previous slides, you mentioned that the marginal likelihood is sensitive to the prior choice. So I was wondering, is there any general criteria that can help us to check, okay, this prior works better in this case?
Yes, there is a whole research in statistics called data prior conflict, where you're effectively trying to figure out how do you check your prior in such a way that it's not in conflict with the data that you observe. Again, there's a whole research trying to basically figure out what kind of reasonable price you might want to look at. How do you check for the data prior conflict? Like if you specify certain prior, generally what people do in practice is that if you know something about the problem, you specify a prior, you can sample from the prior distribution, you can sample parameters of your model, and given the parameters of the model, you can generate the data, you can sample the data, and then look as the samples from that generative model, do they look like something you'd expect in reality? That's one way of checking how reasonable your priors are. Right, so this is sort of general, but there is no sort of, again, your price, your beliefs about the model, something you should think about how you incorporate that incorporate your prior knowledge into the prior.
The prior is independent of the data, so...
Prior should be independent of the data, that's right.
Thanks.
Yeah.
I think there's something called empirical ways.
Yeah, we're going to get to that, yes. Yeah. Okay. There was one more question?
That's my question.
Okay. But here I just wanted to show you that, if you do specify the priors, let's say, over the hyperparameters, and we compute the predicted distribution, it turns out that this integral becomes intractable, even when everything is Gaussian. So you need to approximate, generally speaking.
Can you explain why that is the case when everything's Gaussian? Because in that case, I should just get gains.
I think that so if you think about if this is Gaussian, that you can approximate. But it turns out that the relationship between these guys when you're integrating this guy out, and these guys are not quite in the same sort of relationship, just like in a simple case where you have a Gaussian prime and a Gaussian likelihood. So it turns out for these models you can't integrate. Now, the Bayesian approach, the full Bayesian approach, would be to integrate with respect to the full posterior. The full posterior will be hyperparameters as well as the parameters of the prime, as well as the parameters of your model. And this can, in principle, be done using Markov chain Monte Carlo methods that we will consider later. But for now, we're going to be looking at something that's called evidence approximation, which is much faster. Okay? But you have to make some approximations. Okay. So let's look at the evidence approximation first. If we assume that the posterior hyperparameters, these alphas and betas, remember this is the noise and that is the width of the prime. If they're sharply picked, right, around particular values, then we can make the following approximation. We can say, well, the predicted distribution is going to be approximately the same if we just look at the point estimates of alpha and beta. Okay? Instead of considering integrating over the values of alpha and beta, we're just going to replace them with point estimates. Right. If we have these point estimates, what's the good estimates here, then this integral can be computed exactly. Right? Because this is a Gaussian, we're good to go. Okay? So, and you can think of these point estimates as the mode of the posterior distribution over the hyperparameters. There are two things going on. If the mode of the posterior distribution is sharply picked, then that would be a good approximation. If the mode of the posterior distribution is not picked, sort of broad, that has some width to it, then that wouldn't be a good approximation. Right? But the idea behind this particular framework is that what we're going to do is we're going to integrate all the parameters of the model, but we're going to maximize all the hyperparameters. Okay? So this is sometimes called empirical Bayes. This is also sometimes called type 2 maximum likelihood or evidence approximation. Okay? And again, the idea here is that you're integrating out your parameters, but you're optimizing over your hyperparameters. Okay? Now, there is one sort of philosophically speaking, what's going to happen is we're going to look at this approximation, right? So we're going to look at this approximation, and we're going to say, what are the values of these parameters such that this evidence is maximized? So a little bit of problem here, and some people don't like that particular approach, is because what you're effectively doing is you're going to be maximizing your hyperparameters or choosing your hyperparameters based on the data. And that's something that in the proper Bayesian approach you wouldn't do, because you need to integrate all the parameters. In this particular case, you're going to be looking for these hyperparameters in such a way that they explain the data the best, so that your marginal likelihood is the best explanation to the data. So you're effectively going to be fitting, to some extent, hyperparameters based on observing the data. Okay. So let's look at how it's done. Yeah, question?
I think you're assuming that so the hyperparameters alpha and beta are sharply picked. So does that restrict your choice with the priors?
So in this case, as you will see, we will not actually, we will make an assumption that the priors are flat. So let's get there. So remember from the Bayes rule, the posterior of the hyperparameters is going to be given by the likelihood times the prior. If we assume the prior of the parameters is flat, and that's the assumption that we're going to make, uninformative, uniform, right? Then the posterior is going to be proportional to the likelihood. Okay? And then what we can do is we can get the values, these point estimates, by maximizing the marginal likelihood. And look at the maximization of the marginal likelihood of t given these values. Okay? So that's something that we can in principle do here. So that will allow us to get the values of these hyperparameters from the training data. And that's why people sometimes call it type 2 maximum likelihood, because it's kind of you're doing maximum likelihood over the hyperparameters by integrating out your parameters. Sometimes it's called empirical base, and the word empirical base sounds a little bit funny. A lot of people don't like it. It's just empirical. It's not the truth, but nonetheless, in practice, it actually works fairly well in a lot of cases. Now, one thing you have to remember is that this ratio, alpha over beta, is essentially the same as the regularization coefficient. So what happens in these models is sort of what you're trying to do is you're trying to find essentially the best regularization coefficient for your model. Essentially what's happening here. Now, let's look at some math behind it so you get some intuition as to how this can be done. Now, remember the marginal likelihood is obtained by integrating out parameters. So this is something that we can do explicitly. Right? Given alpha and beta, we can compute the marginal likelihood. Just to give you a little bit of notation, the marginal likelihood, we have these terms coming from the two Gaussians, and you have this term, and these are just the two terms being combined. This term comes from the likelihood, this term comes from the prime. I'm going to show you the math, but I think I encourage you to look at the book, and again, one of the homeworks you'll deal with that. But again, remember, it's the likelihood times the prime. This term, the first term comes from the likelihood, the second term comes from the prime. Okay. Now, using static results of the Gaussian distribution, it turns out that the posterior distribution has an explicit form, has this form here. Again, these terms, and this is the same as this error, but where it's a function of the predicted mean, which is easier way to write it. So this is something that we can compute, and let's look at the sum fits to the data. Just to remind you, remember in the last class, we've looked at 9-degree polynomial, well, the sine curve here, and here's what happens if we fit 0 degree, 1 degree, 3 degree, 9-degree polynomial. Right? And remember, the 9-degree polynomial perfectly explained the data. The 3rd-degree polynomial was a reasonable explanation to the data. If we look at the marginal likelihood for this data set, and where these parameters were actually fit to the data, if we look at the marginal likelihood, notice what happens. This is the degree of the polynomial. Right? And this is the marginal likelihood. So the marginal likelihood at 0 is pretty small. If you fit a 1-degree polynomial, just a line, the marginal likelihood goes up. The 2nd-degree polynomial, which is the parabolic function, actually doesn't fit, it doesn't explain the data well. A 3rd-degree polynomial picks up. A 4th-degree polynomial goes down, and look at the 9-degree polynomial. Right? So the evidence, the marginal likelihood for the 9-degree polynomial is actually pretty small. Right? So this essentially tells you the trade-off between how much you fit to the data versus how much you get penalized for the complexity of the model. You can see that. So in principle, by looking at this graph, you can get the intuition that, well, marginal likelihood tells you something about the choice of the correct model for that particular example. And it's sort of in this particular case, it chooses the 3rd or 4th-degree polynomials. It thinks that 3rd, 4th-degree polynomial should be a reasonable fit to the data. And the evidence here favors the model which is a 3rd-degree polynomial. Now, let's look at maximizing the evidence. So how do we do that? Turns out that this just becomes a very simple optimization problem. Because what you're effectively doing is you look at the marginal likelihood, it has an explicit form, right? And then we're going to maximize the evidence with respect to parameters alpha and beta. And that just becomes, you differentiate with respect to alpha, differentiate with respect to beta, and you solve for it. Now, it turns out there's no closed form solution, so you have to iterate. And let's look at how this can be done. I'm going to give you a set of equations. And the only reason why I'm giving you that set of equations is there is one quantity that will come out of it that will have an intuitive explanation as to what's going on. So bear with me. You don't have to follow all the math. I assure you it's quite simple if you actually do it yourself. But the idea here is very simple. Let's look at the eigenvector equation. So remember, these are basis functions. we're going to look at the eigenvalue decomposition of this matrix, phi transpose phi. Think of it as a covariance matrix. And so now, if I look at this matrix, which is alpha identity plus this matrix, it will have eigenvalues alpha plus lambda I. So this is just the precision matrix of the Gaussian posterior. Now, the reason why I'm playing with these eigenvalues, eigenvalues decomposition, is because I need to differentiate the log of the determinant of the matrix. And as you know, the log of the determinant is the log of the product of the eigenvalues. Right. If I take the log, it's going to be sum of the log of the eigenvalues. So now I can differentiate with respect to parameter alpha. That's the reason. Right. So basically, that gives me the expression that if I want to differentiate log of this guy, log of the determinant of this matrix with respect to parameter alpha, with respect to parameter beta, I can use that equation here. Okay. Now these eigenvalues will be of very, they'll have a certain meaning as we get there. So just remember that the marginal likelihood has this form, where we've defined this term, the error term, as this thing here, and now differentiating with respect to the alpha, which is again the precision of the prior. It's sort of we can just differentiate, and you obviously can see to differentiate the first term. It's m over 2 over 1 over alpha. If you differentiate with respect to alpha, you get this term appearing here, and if you differentiate log of this guy with respect to alpha, you get this term here. It's just very simple, basic algebra. You can do a little bit of manipulations, and it turns out that you can define the following quantity, which we're going to call gamma. And gamma is sometimes called the effective number of parameters in your model. Right? And it's defined as the eigenvalues divided by the eigenvalues plus alpha. And we will have a much better understanding of what that means. But that's an important quantity to keep in mind. Somehow it tells you how many effective degrees of freedom you have in your model, or how many effective parameters you have in your model. Okay. Now, again, the station point with respect to alpha satisfies this, where gamma is defined as effective number of parameters. And one thing to note here is that these eigenvalues, they only need to be computed once. You don't need to do these computations over and over again. It's just eigenvalues of the covariance matrix. So then you basically iterate. You compute alpha, you compute the gamma, you re-estimate these terms, which are dependent on alpha. You recompute alpha, you recompute gamma, and so forth. And you can show that you converge. Effectively, what you're doing is you're doing gradient descent in the alpha space. It's just, in this case, it's a coordinate descent. And the same thing if you differentiate with respect to beta, this marginal likelihood with respect to beta, and you get this thing. Now, this looks like variance. Right? What does it look like? This is your data point. This is the estimated posterior mean of your parameters. So this is the mean of the posterior. So this looks like variance. And that's exactly what you'd expect it to be. One difference here is that you're dividing it by 1 over n minus gamma, which is an interesting quantity. So basically, when you estimate the variance, you divide it by n minus 1. Right, so in this case, you're dividing it by n minus gamma. Now, what is the idea behind this quantity gamma, which is the effective number of parameters? Let's look at the following example. Okay? So, this is our prior. It's spherical. It's centered at 0. And this is our likelihood function, or you can think of it as, quadratic likelihood function. Because we're looking at the squared losses, so this is the quadratic likelihood function. The eigenvalues, lambda sum I, what they do is they measure the curvature of the likelihood function. And this quantity gamma is going to be a number that lies between 0 and m. So m is the number of parameters in your model. So if you think about 9-degree polynomial fitting, then m gamma is going to be between 0 and 9. What happens if your eigenvalues are much bigger than alpha? If your eigenvalues are much bigger than alpha, then that means that the corresponding parameter w sub I will be close to its maximum likelihood. Right? The reason why is because this term will be close to 1. And that's why these parameters are called well-determined parameters, because the values are highly constrained by the data. On the other hand, if these coefficients, these eigenvalues, are much smaller than alpha, then the corresponding parameters will be close to 0. They're effectively going to be pulled by the phi towards 0. Okay? As well, this ratio is really close to 0. So it's effectively, if you look at this example, so let's look at this example, for example, that be a little bit more illustrative. This is our maximum likelihood estimate. This is a prime mean. So obviously, in the Bayesian framework, if you're looking at regularization, your estimate is going to be somewhere between 0 and your maximum likelihood estimate. The posterior mean is going to be somewhere between those two. If you look at this U sub 2 direction, U sub 2 direction is very constrained. It's very hard for for the parameters to move all the way here, because they are constrained by the Gauss, only very, very improbable. So that's why, this map estimate moves down a little bit, but not too much. On the other hand, this direction is much less constrained. And because it's much less constrained, the phi effectively pulls it closer to 0. So this direction is very constrained. This direction is less constrained. So along this direction, the phi is going to be pulling it towards 0, which makes sense. Right? If your likelihood curvature would look like this, then it would say, well, actually 0 is also probable under this model, so you pull it towards 0. So in this case, gamma here effectively measures the effective total number of well-determined parameters. Right? Parameters constrained by the likelihood. And all of those directions that are less constrained, the phi is going to be pulling those parameters towards 0, which makes perfect sense. Because in the less constrained directions, you want to move your parameters, you want those parameters to be close to 0. Now, in the limit, as n becomes much bigger than m, then you can basically just do the simple approximation. This is effectively saying that the precision is just going to be given, or 1 over alpha, which is the variance, is going to be given by look at the posterior mean, compute the variance of the posterior mean. Right? And this is just will be look at the variance and just estimate the noise based on the variance. I mean, this is something that you would do without resorting to the evidence approximation framework. Right? This is something that you just do based on you fit the posterior mean and just will figure out what the width of the posterior mean is, how much spread there is. So these are quantities easy to compute. Again, this only holds in the regime when you have a lot of data. But then, generally speaking, if you have a lot of data, then in most of the cases, your posterior mean is going to be tightly picked, probably around maximum likelihood estimate. Right? So Bayesian models are mostly useful when you don't have a lot of data, generally speaking, because you can put some prior knowledge about the values of your parameters. Now, some of the limitations. If you look at n basis functions, if you put n basis functions along each dimension in d-dimensional input space, that would require m to be d basis functions. Right? And it's sort of like something that's called recursive dimensionality. So that's generally something that you can do. I mean, we've looked a lot into basis functions, right? And trying to represent your data in terms of the basis functions. That's generally not useful. Now, we can get away with few basis functions by choosing is using training data. So for example, there's a whole class of models that's trying to adapt the basis functions to the data. These are functions, these are 5 variables, right, that have their own parameters, like a mean and a width. And that's something that we'll see later. And the other thing I just want to point at the end of today's class is that data vectors typically lie close to some nonlinear low-dimensional manifold, right? Because dimensionality is going to be smaller than that of the input space. In which case, you might want to discover what that underlying manifold is. And again, that's something that we'll probably look at the second half of the class. Okay, that's it for the Bayesian models today. So next class, we're going to jump into models for classification. Okay. And so far we've looked at. I encourage you to look at the book. So far we've looked at the linear models for regression. We've looked at the Bayesian models for regression. Next class we're going to look at the classification, and after that, we will finish the introductory part of the lecture, and then we're going to get into graphical models, mixture models, and a bit more advanced topics. Okay.